looking at an application for solving exponential equations, one comes in the form of finding the age using carbon-14 dating. Here I have a piece of ancient charcoal contains only 30% as much radioactive carbon as a piece of modern charcoal. If carbon-14 has a half-life of approximately 5,730 years, approximate the age of the ancient charcoal first by graphing calculator and then by solving the equation. Now, an equation that we can use to do the carbon-14 dating is a half-life equation where the amount of the radioactive material present currently is equal to an initial amount times the quantity 1/2 to the T over H power, where A sub 0 again is the amount that's initially there, T is your time that is in the same units as H for your half-life. So H is the half-life of that radioactive material. Now this can take a couple different forms. Another form that's commonly used is if we write this as A is equal to A sub 0 times 2 to the negative T over H power. Remember, a negative exponent means to reciprocal the base. And so 2 to the negative T over H power is exactly the same thing as 1/2 to the positive T over H power. Now half-life is the amount of time it takes for the radioactive material to have half of what it had. So if I have an initial amount, it would take 5,730 years for the carbon-14 to be half of what it had. But then that's the start amount for that period then, and so it takes another 5,730 years to be half of that, and another 5,730 years to be half of that. So theoretically, it's never really gone. When we think about this being 30% as much radioactive carbon as it had to start with, well, 30%, I had to go through one half-life to get to 50% as much, so that's a 5,730 years. Now, if I do half of that, that would be 25% of what the overall originally would be. So we're talking about a fairly big number here. Let's see what happens when we solve this by our graphing calculator and then by using our equation solving techniques. So for the graphing calculator, the first thing we look at is the amount now says that it's 30% as much radioactive carbon as a piece of modern charcoal. So the amount now is 30% as much as the original amount. And remember, H is 5,730, so I can put that in. Now, it originally had carbon-14 in it, so A sub 0 can't be 0. Then I can divide both sides by A sub 0 and get that 0.30 is equal to 1/2 to the T over 5,730 power. And again, I can divide both sides by A sub 0 because I'm not dividing by 0, since there was some carbon-14 to start with. So when I'm solving this for a graphing calculator, I'm going to go to my y equals, and in the y sub 1 equals, I'm going to put in the left side, this 0.30. And in the y sub 2, put in the right side, open parentheses, 1 divide by 2 to the, and then open parentheses, T divide by 5,730. Now, a couple things you could do here. You could put in 0.5 instead of the 1 divide by 2, because that's the same thing as a half, to the. And if you have a calculator that sits up in the exponent, in its spacing to put in the exponent, you don't need parentheses. But if you have the older calculators where you just get that caret, you do need to grab parentheses so that whole thing stays up there. Now what we're going to do is find out where these two graphs intersect, because where they intersect is where they would be equal, and that would give me the value there. And I do need to make one correction. on your calculator, you're going to actually just put the letter X there. We know it's for time, and we know that that's what it's going to represent, but the calculator entry is going to be the letter X. Now we need to window this so that we can see our solution. So think about your y sub 1, that's 0.3, so that's a value between 0 and 1. So when you think about your y values, we'll get to in a minute, they're just going to be a very small span. But the x values are the time. And like we talked about with to get to 30% that's remaining, that's going to be a long span of time. So for your x min, go ahead and put 0. But for the x max, we're going to put 11,000 in. So I roughly looked at doubling this, just shy of doubling it. And then for the y min, put in 0, but for the y max, put in 1. And where you do that for your window, it's when you're looking at just setting it up with the window button right next to the y equals. Okay, now you should get two equations, or two, when the window part of it, now you're going to push graph. And you should get the graph where you have a horizontal line, and then you have another curve coming, and you want to see where they intersect. So then when you push second to get to the calculate, so second calc, you want to pick intersect to see where they intersect. Now it's going to have a cursor that's on one of the lines, and it'll say first curve, just push enter. And then it'll pop that cursor to the other curve, and it'll say second curve, just push enter. It'll then say guess, just push enter again, and it will go through and find the value, and it'll come out with a value that's about 9,952.8 years. Or about 9,953. And these directions I've been giving you are on like the TI-83, TI-84 calculator. Now how about to solve the equation? Well, we're going to come back to doing the first steps. We replace A with 0.3 times A sub 0 because it's 30% as much as the original amount. We're going to divide both sides by A sub 0 again, and we'll have at the stage of 0.30 is equal to 1/2 to the t over 5,730 power. Now this time we want to think about solving exponential equations. And I do have a separate video that I've posted that has like solving different exponential equations. Here, the letter we're trying to solve for is t. It's caught up in the exponent, but the exponential expression is equal to a number. So since that's true, we're just going to take the log of both sides, and I can take log base 10 or log the common log, log base 10, which is the common log, or the natural log of both sides. Let's just go ahead and do the natural log. Now what that allows me to do is to bring the exponent down. So it's the natural log of 0.30 is equal to t over 5,730 times the natural log of 1/2. And then again, we want to solve for t. So the first thing we're going to do is we're going to multiply both sides by 5,730 to get rid of the fraction. So 5,730 times the natural log of 0.3 is equal to t times the natural log of 1/2. And then lastly, divide both sides by the natural log of 1/2. So t is equal to 5,730 times the natural log of 0.3 divided by the natural log of a half. And when you look at keying that through your calculator, you'll find that that's approximately equal to 9,952.8 years. So either way that we go about this, using the graphing calculator is handy before you actually get to the point where you've learned how to solve exponential equations. But going full circle, after you learn how to solve exponential equations, you'll see that you get the same value there in your solution of this particular problem.